All right, good day, ladies and gentlemen. We are going to be looking at normal distributions and establishing whether or not a distribution is normal. So we're going to have data, and how do we decide if it's a normal distribution or not? How do we decide if we can use these z-scores, these standard scores, to predict a percent that's within a certain range of values? So what we want is a way to do that. There are a lot of statistical procedures that are based on normally distributed data. We have to be able to deal with this. So here's our strategy. First off, plot the data. Look at it. Make a dot plot, a stem plot, a histogram. See if it is approximately symmetric and bell-shaped. If it's not, if it's clearly not going to be symmetric, if it looks like a staircase, going up to the top and then stopping, it's not going to be normal. So this should be where we start. We can rule out a lot of data sets just by looking at a visual depiction of that data. So if it is roughly symmetric, that doesn't mean it's normal. We have to make sure that it fits with this empirical rule, this 68, 95, 99.7 rule. If the data does fit with that, then we can say that it is a normal distribution, or roughly normal. So we're going to count how many observations fall within 1, 2, and 3 standard deviations, and look at what percent of the whole data set those represent. And if they fall close to these percents, we're good to go. And then we'll look at normal probability plots using our graphing calculator, our TI Inspire calculator. You can do this in really pretty much any statistical software. But what we're looking at is what the data values would be with a z-score paired up. What do we expect the z-score to be? And if it matches to a nice straight line, that means that our data is normal. So if the points on a normal probability plot lie close to a straight line, the plot indicates that they're normal. Systematic deviations from a straight line indicate a non-normal distribution. Outliers will be points that are far away from the overall pattern. Okay, so what's that look like? Well, here's a set of data. Survival time in days versus how many people survive that long. So this beginning part, if you look at that, if we ignore all of this over here, that looks roughly symmetric. That's sort of bell curve-ish right here. And if you look at the beginning part of this graph, it's roughly linear. Right there is sort of a straight line. If we were to go like that, it's sort of a bell curve. So it does a decent job. But then notice as we go out further this way, it is very clearly skewed to the right, and we have these points dribbling off over here. No longer a straight line. This is not a normal distribution. So let's do an example here before we get to this summary. We're going to look at the unemployment rates for the United States for each state November 2009. And here are the unemployment percentage rates for each of the 50 states. We're going to go through this process and look at how we can tell if this is normally distributed data. We'll plot the data, we'll check whether the data follows this rule, and then finally we'll construct normal probability plots. So plot the data. Let's go ahead and switch modes to our graphing calculator. And we're going to type in this data. So go here and you're going to have to type in these data values. The best way to learn how to do this is to actually do it. So pause the video, type in all 50 data values, and then restart it, and here we go. So we have our data values. First thing we do is we make a graph. We're going to plot this data. So I'm going to go over here, add data and statistics. I'm going to come down to the bottom, add, and percent unemployment. There's my dot plot. I mean, that sort of looks normally distributed. It sort of looks symmetric. I can get a better idea whether it's symmetric by looking at a histogram. Control, menu, while my cursor's in the front, in the middle here, and I'm going to go histogram. And there we go again. sort of looks symmetric. It goes up and then back down. There's no huge differences. This bar looks a little out of place, but overall it looks pretty symmetric, pretty evenly distributed. So I'm thinking, yeah, this looks like it's going to be a normal distribution. It might be. Well, before we can say that, we need to identify what the intervals would be where we're 1 standard deviation, 2 standard deviation, and 3 standard deviation away from the mean. So I'm going to go back to my data. I'm going to perform my stat calculations. One variable stats. I'm looking for the mean and standard deviation. My data is in percent unemployment. I can put my results in column C. There we go. My mean is 8.68. My standard deviation is 2.22. So what are the intervals that we're looking at now? Well, the intervals that we're looking at are mean plus and minus 1 standard deviation, so that would be this. If I have 68%, I have 68% of all my data values, or close to it, within this range. Well, there's 36 out of 50 that fall within these values, which is 72%. I mean, not great. It's kind of close to 68%, but not great. Let's look at the interval, the mean plus and minus 2 standard deviations. So that would be everything from 4.232 to 13.132. If we count that up, there's 48 out of the 50 states, which is 96%. And if we look back at the empirical rule, we're expecting 95% of them to be in that interval. So not bad. How about 3 standard deviations? That would be this range of values. That's 50 out of 50. That's 100%. So these percentages are fairly close to 68%, 95%, 99.5%. And from this, we could say that our data is roughly normal. We have an approximately normal distribution for this data. But there's another way we can tell we can make this normal probability plot. It's a little bit quicker than using our empirical rule and counting all these things. What we're going to look at, it's also called a normal quantile plot. We're sort of looking at percentiles versus z-scores and how the data is distributed. I'm going to go back to my calculator. I'm going to go back to my graph, and while I'm in the middle of the graph here, I'm going to hit Control, Menu, Normal Probability Plot. And we can see here that although a few points aren't very close to the line, the vast majority of them are very, very linear in nature. They're following this line very, very closely, and because this normal probability plot is mostly linear in nature, we have established that our data is approximately normal. The closer the points are, the better the data is to fitting a normal distribution. So, here's a summary of section 2.2. We have our normal distribution. We have the empirical rule. Standardized normal distributions have a mean of 0, a standard deviation of 1. That's when we're getting z-scores. Remember, people, we can use table A to go from z-scores to finding percentages, and we can assess normality with what we just talked about. Before I leave you today, I want to summarize some things in this section with a quick flow chart. Oftentimes in these problems, we start with data. And we want to take that data and turn it into a standard score, a z-score. And the way we do that is we take z equals x minus x bar over s. X minus the mean divided by the standard deviation. And then ultimately our goal is usually to find a percentage that goes along with it, an area under that normal distribution curve, and we're using table A to do that. Or we can make one big jump like that with norm CDF in TI Inspire calculator. Other problems ask us to go the other way. We start with a percentage, and we want to change that into a z-score so that we can change it back into actual data. So what we're using is table A again, but this time we're starting in the middle with the 4-digit decimals. And then once we locate the z-score around the edges of it, so coming down this way, we're looking at the edges, start at edges. The z-score, and then we look in the middle for the percentage. Once we have our z-score, we rearrange this formula, and we know that x, our data value, is our mean plus our standard deviation times our z-score. And again, we could use the graphical calculator, our TI Inspires, to get all the way back up here in one shot, and that's with the inverse normal. Command in our calculator. So this flowchart should hopefully help you to identify a strategy for going through these problems. And that is where I shall leave you. Have a wonderful day. I shall miss you all dearly until we meet again.